So we're going to give a couple more minutes before I actually begin the talk. But before we did that, I thought we could cover a couple of preliminary things. So I've had a chance to chat with a few of you. This is once again the beginner track, quote unquote beginner. I'm still a beginner, still learning stuff about functional programming and immutability and everything every time I go hit Google. But it is the beginner track. We're going to be covering immutability. That's going to be where we start, not where we end. We'll talk about immutable data structures, what they are, why maybe they're important, and then we'll start to use them, and especially consider them in the context of if you work in an environment in which all the constructs that you have are mutable, how do you deal with immutable data structures in a functional way? So that's what we're going to be talking about here today. By a show of hands, how many of you are familiar with and regularly have you're conversant in JavaScript? Maybe. Okay, fantastic. So that is the language that we're going to be using today on the slides. You should follow along whatever language you're comfortable with, assuming that you can kind of map from JavaScript, which should be straightforward unless you only know Lisp, because they're totally different. Syntaxes might throw you. But you should be able to follow along whatever language you're comfortable with. And in the event that you happen to use a language that already has a lot of the cool constructs we're going to work with and talk about, I would suggest not cheating in using those, but try to create bad ones that you can work from so you can kind of like logically learn how we get from bad data structures to good data structures. Bad, good, in terms. Now, the good thing for all of you is that this is immediately after lunch, which means that no matter how bad this talk is and our workshop is going to be, you're not going to know about it because you're going to fall asleep about halfway through it. The bad thing about that is that you're going to fall asleep halfway through it, which means you're going to miss half of what I say. So I'm going to try to load some of the important stuff up front, and then what we're going to do is we're going to work through problems. We're going to go through a format which is I will explain some stuff, we're going to work through some actual problems, so get your laptops out, be ready to type. In the initial problems or code examples, I'm actually going to work through with you, and then the later ones you're going to work through on your own. I'm just going to give you method signatures. I'm going to say go do it. What I'd strongly suggest is you're going to benefit more if you start looping in the people around you. Okay, islands fail, but small communities tend to grow and grow stronger. So look around you. These are the people you're going to be working with over the next 2 hours, and the people who might be able to keep you awake in the midst of this lecture. We are going to be having a 15-minute break about halfway through. So if you need to use the restroom, get more water or whatever, if you kindly wait until then, that'd be great. If you can't, nature calls, so don't worry about it. With that, I think we should go ahead and get started. We're a little after 5 past, and I don't want to waste your guys' time. We will try to preserve a block of time at the end of this session for questions and answers. So to begin with, immutability, beginner's guide. I like to call it Immutability 101. And we're going to be talking about what it is, why maybe they're important, and then how we're going to use them. Which brings us to me. Who am I? My name is Paul DeGoes. I am, in fact, one of the younger brothers of our conference chair, John DeGoes. So my tag here, I am Brother Paul. You can call me Brother Paul. I'll take that. My contact information is found here. This workshop is actually online. It's on my GitHub account, so you should feel free to head there now. I'm going to leave this up for a minute in case you want to go out there and pull down the slides. I would ask you, do not advance in slides ahead of where I am. Don't cheat, because the answers are further down the slides for some of the problems. So try to stay on there with me. But if you want, you can actually copy and paste some of the code from there. It might be useful later on. You can also give it to your friends and say, hey, there's code examples. This is what we learned. So what else do I do? I'm actually a software engineering manager for a company called Living Social. I manage a group of about 7 engineers right now. And we work on mostly web backends with some front-end work. I started as a front-end developer, and that was about 6 years ago. So the lesson for those of you who are here today and don't know much about functional programming or consider yourselves beginners as I still do, is that if you work really hard and keep learning, nothing is impossible. I never thought 6 years ago I'd be managing a group of engineers, some of whom are actually smarter than I am, to build really incredible things, and yet I do that today. And I know that applies to all of you. You're here, so a big congratulations to all of you, since you already know the direction that stable, reliable code is going, in a functional direction. So welcome to LambdaConf. So I was told that the key to a successful presentation was cat pictures. And I'm supposed to have some sort of deep metaphor here for what the kitten is and what Godzilla is that has to do with immutability, but I don't. So all you get is a cat picture. Now let's talk about immutability. Well, what is it? Basically, this comes from the Latin immutabilis, meaning not and to change. So very literally, it just means something that doesn't change. In programming terms, what we're really talking about is an object, the state of which does not change after it is created. Now, I want to talk for a second about state. What is state? Somebody tell me what state is. Oh, great.
Bad.
No, state is not bad, but that's not a bad answer. It's a funny answer. State is everywhere, right? State is your code. Your code is state. State is unavoidable, but when dealing with state, especially in terms of code, oftentimes it is very helpful to ensure that the state doesn't change, and we will talk more about why. So when we talk about two different kinds of state, we'll talk about mutable state, that is the state that's in flux, or you can modify it after it's created, an immutable state. In other words, once you create that thing, it can't be changed. And this has to do with mathematics, which for those of you who were lied to when somebody said, no, programming's not about math, they lied. It is all about math. Functional programming is especially about math. But essentially it has to do with the fact that for a given function or method, you can pass in the same arguments and you will always get the same response. And if you don't have that, then you have mutable state. If you do have that, then you have immutable state. You should also feel free to interrupt me if you have any questions during this slide. So what I want to tell you today, first of all, is that this is not a foreign concept. In fact, you deal with it every day if you write JavaScript or any other language. You deal with immutable objects, immutable state all the time. In fact, in JavaScript, the string numbers here are immutable. So you can create a variable, set it to 1, var x is equal to 1. X is indeed equal to 1. You can add x to another number and get a different value, but if you check and see what x is after the fact, you're going to get x, which was 1 to start with. So in JavaScript, numbers are in fact immutable. What are some other immutable things in JavaScript? Strings. Exactly the same way. Once you create a string, you cannot change it. These are one of the fundamental data types of JavaScript. You create it, there's nothing you can do after the fact. You can even call a substring on it to try to get a part of it, but that does not in fact modify the string itself. It gives you a new copy of that string. What else? Well, the other data type, Booleans. Booleans cannot be changed after they're created. You make them once, you can use them, you can add them together, you can operate on them, but no operation on a Boolean will ever change the value of that Boolean. Does that make sense? Nod your heads with me now. Good, excellent. We're all on the same page. So now answer this question for me. How can a variable be immutable? If var x can be assigned to be a Boolean, we can verify it's true. We then say x is equal to 1, we've reassigned it, or we can make x equal to a string that is anything. So in fact, if x can be anything, how is it then immutable? That is, it cannot change. Here's a question for you. I'm lazy. In the corner.
Because the variable is simply a pointer, the data doesn't change.
The variable is a reference pointer. It's pointing to a chunk of memory. The chunk of memory has not changed. Rather, the reference has changed. So exactly right. Variables are immutable. That's why they're called variables, because they vary. The value of a variable can be immutable. Does that make sense, the difference between those two things? A variable is a pointer to a value. Some values can be immutable. Does that make sense? I'm going to take that as a yes. Thank you. All right, so values are immutable. So now we should talk about why immutable variables, why immutable data structures are in fact valuable. And in a simple phrase, I can tell you that they are valuable because they are easier to think about. They are easier to reason about. That's why we like these things principally as software engineers. I don't know about you, but I only have so much brain space. And it doesn't matter how smart you are, you still only have so much. And the easier it is to think about something, the more you can spend your mental CPU cycles focusing on something else, ideally something more interesting. So why are they easier to reason about? Because one, they operate uniformly. Let's see this in action. So let's assume we create a variable, and you can type this in and follow along with me if you want, or just follow along on the slides. Create a variable, last week's dollars. We set that to 6. We create another variable, more dollars. We set that to last week's dollars plus 2. Well, what we would expect then is if we check more dollars, it's going to be 8, right? Because 2 plus 6 is 8 most of the time. And if you check last week's dollars are still going to be 6. That's a good thing, right? So now let's consider a different data structure other than the immutable number we just considered. Let's consider, in fact, a mutable array. In JavaScript, arrays and objects are mutable. So now let's set last week's dollars to an array of 2, 2, and 2. Let's actually say these are like your last multiple weeks. You got paid $2 a week, your migrant labor. So we paid you $2 every week for the last weeks. And now we're going to add more dollars. So we take our more dollars, and we do last week's dollars, and we push in 2 more dollars. We now check your more dollars. What is it going to be? What will more dollars be here? 2, 2, 2, 2, 2, right? 2, 2, 2, 2. We should expect that, yes? And last week's dollars is going to be? 2, 2, 2, 1, 2. It should be 2, 2, 2, right? Not in JavaScript. In JavaScript, more dollars is 4. And last week's dollars are now 2, 2, 2, 2. So what this tells you is that you mentally in JavaScript have to keep track of the fact that, oh, this thing over here operates the way I would expect it to. But over there, if I use that mutable data structure and I do something to it, I need to make sure I didn't change it in some fundamental way such that it may not be useful to me anymore. So why should you care about making immutable data? Because they're easier to think about. They operate uniformly. Why else? Because they are what they are. There are no mutations. Let me give you a very simple example. For those of you who have worked in large and complex code bases, which I know none of you have, you realize that there may be a variable or a reference or a function in one part of your program that is referenced thousands and thousands and thousands of lines later somewhere else. So my question to you is, as one of the people who cares about what comes out of this, do you really want to have to keep track of all the possible places that thing that was created over there might have been changed along the course of those thousands and thousands of lines of code? For instance, let's say you're paid X amount, and that is set somewhere in one line of code, but some developer in the middle of this stream, before you actually get paid, has decided to operate on that in a way. And they've actually mutated the original value. Now you're not getting paid X dollars, you're getting paid X minus X dollars. And as a result, you don't get paid at all. So as the developer at the end of the function, you really want to make sure that there are no changes to something in code. And you have the mental overhead of knowing every possible usage and every possible state change and every possible reference in code. And you got to check all those things to make sure no one did anything with it before you got a hold of it, before you can even use it. Now, does that sound like fun to you? No, it does not. So you should care because they are easier to reason about. There are no surprises to immutable variables. And immutable variables also just always are what they are. So you don't have to care about the possibility that they can change. So what do we do now? If we can acknowledge, actually let me take a step back and ask a question. How many of you are persuaded that immutable objects have some value at this point? Okay, there's a holdout right here. So everyone else seems to be reasonably persuaded. Let's then ask the question, what do we do? If we want to create mutable data structures, and especially if we want to create them or use them in an environment in which maybe they are not native, aka JavaScript or Python or Ruby or lots of other languages, what do we do? Well, I have a 3-step plan for you. These will solve all of your problems. If you follow them, you will make $1 million. You will be perfectly happy, and all of your code will be endlessly flawless. The first is to admit that mutation is evil. And we can all say it together here. Mutation is evil. State is not evil. Mutation is evil. Now, we say this with a qualification because under the hood, ultimately, all code is a bunch of zeros and ones that are changing, right? So really, this is about not exposing mutation, not allowing mutation to be part of your interfaces. So we acknowledge mutation is evil. We stop creating it. We stop writing programs that create mutation. When you write a program, when you write an object, you make sure nobody can change it. So then that developer who has to work with your construct 10,000 lines later is like, oh, cool, I can't change this thing, therefore I know what's in here. That's helpful. Stop making it. And lastly, you start creating immutable things, which is what we're going to work on for the remainder of our time here. So I appreciate your patience as we walk through this. Hopefully you're persuaded of the value. We're now going to start working on problems together. The first problem is going to be we're going to generate an immutable list. An immutable list. So we've already talked about in JavaScript you have an array. That is a mutable list. It's a series of items that are in a container. You can mutate it. You call push on it. You call, pop, push. Actually, most of the operations on arrays they mutate them. Unshift, for instance. So we're going to build ourselves an immutable one that does not change, a replacement for the JavaScript array type. This is our task. Create a replacement for the JavaScript array class that does not mutate the initializing value, if present. So you're going to pass something into it, presumably. You may want to pass in an array, for instance, to create this thing. You want to ensure that we do not expose mutative methods. So you're going to give us a couple of methods on there that make this thing useful. And those methods are going to be push, so you can stick stuff into it, unshift, which is we're actually going to put something on the opposite side of it. So push inserts something at the front of the record set, and unshift is going to stick something at the end. CanCat joins two different lists together, and then length tells you how long it is. We're also going to give you some sort of index operator so you can select an element at a certain index. Okay. This should make sense to you if you've worked in most languages. This should all make sense. If it does not make sense, raise your hand. I'll come over and talk to you afterward. So next up, I'm going to write the first method for you. I'm going to give you your function signature. I'm going to create a function list that takes an array. We're going to instantiate a variable on that, which is mutable list. We'll set that to a slice. What that does is that clones the array. It's a simple way in JavaScript to clone an array, the whole array. So we're not going to use the original array. We're going to clone it, create a brand new one. That way, again, we're not mutating the original value. I'm going to add one method for you, and that is length. We'll reference the existing mutable array that's a copy of the passed in one, and we'll get its length. Such that if we call a new list, pass it in, and call length, we get the value of the length of the original array. Pretty simple, right? So now, let's go back here. And here's the chance where we actually get to work in groups. And I'm going to wander around to make sure everybody's doing well. But get together in your groups. I see 4 here. I see like 5 there. And try to work through this problem. I'd like you to create a list that will have these functions: push, unshift, concat, length, and index. And when we're done with this, we'll move on to the next task. And you'll be able to say, for some of you for the first time, I made an immutable object. Nobody can change that thing. All right, so let's go ahead and work on that. And this will give you the method signature and a starting point. All right, I just wanted to check in and see how many of us have solved the problem and have defined. Nice. Go over and talk to those people and this person over here.
We've also got
Nice.
shift. Yeah.
So what you found, let me guess, what you've done is you created your own methods that wrap mutating processes in JavaScript. Yes? So you use the native constructs in JavaScript array, and you just wrap those in methods that prevented you from actually exposing something that's mutated. Let me show you how you do this. We're going to work through this together. Can you see that? This is the answer. And we're going to walk through this line by line after length. Do we need this to be larger? I do not think I can do this. Does anyone know how on Keynote to make the presentation larger? No. Yeah, I was afraid of that. Oh, that sucks. Okay, we'll do that. And let's work through this line by line. Oh, that's not going to work. And this is why I don't do this for a living. All right, can we see this? So the first thing I do here is I'm like, well, I've got a mutable list. So what I'm going to do is I want a wrapper to create an immutable list. This is a kind of helper function. And what it does is it takes my mutable list and it wraps it in this very list itself. So it's a recursive call. This will allow me to generate new lists, should I need them. And especially what it will allow me to do is when I return something from my functions, I'm not going to return that stateful list, the array that was passed in. I'm going to give you a brand new immutable list, okay, which you cannot mutate. That's the goal there. All right, let's do this. I think what I'm going to do is I'm just going to look at this one line at a time. And can we see? Can you see this? This is the array syntax value of index, and I just gave it a name, which is value of index. Give me the member at this index, the value at this index, whatever it is. How do I do that? I open up the mutable list at that index, and I return that value. Now, I don't have to worry about mutation here. Why?
Because you're returning a copy.
Well, yes and no. Even if I wasn't returning a copy, because I've done a slice as my initial value, which is a copy. Even so, this is actually one of the non-mutative functions of an array. So when you look up the value at a particular index in JavaScript, this does not mutate anything. This is one of the challenges of JavaScript. You never know when something's going to mutate something and when it's not. So in this case, no mutation. I don't have to worry about that. Does that look pretty clear? There are no questions. I think that we're all on the same page. Let's go to the next one. All right. Now I added my append function. Now this is, if you're in the closure class, this is the association or assoc. Alternatively in JavaScript, this is your push. And what I'm doing here is I'm first taking my mutable list, and I'm actually going to use that function. I'm going to push something onto it. I'm going to push the new element. But then you'll notice what I'm doing here. I'm not going to return that list. What am I going to do? I'm going to return the immutable list, which is a version of the existing mutable list. And it will copy that data because that's the first thing we do, is it copies the data when you create that list. And it will be the new data that has been mutated. This is probably confusing, but raise your hands if you need help on this. And you can go talk to those people. Okay, no. All right, so this would be a problem. If I allow you to do an append, and I pass out as a result of this the mutated list, then it prevents you from operating on that list in the same way that you could operate on the original list. What I've done is I said, you can operate on my list, but from the operation, I'm going to give you a mutable array. So you can take my immutable list and do something to it, but you don't know what you're going to get back from it. In this case, I may give you back the original array, in which case you're back in the world of mutation. Or, and this is very important when you're going to design classes like this, you want to always ensure you're going to pass back something that's immutable. Remember, one of our guiding principles is not to make mutable things. So I'm not going to give them a mutable array back. I'm going to give them a list. Does that make sense? And an immutable list. Does that clarify that a little bit? All we're doing here is returning the mutated data inside this immutable wrapper of ours. Are we still confused? Good. Let's move on then. So now we've done the push function. Now let's do the unshift function. So in this case, I've chosen, as I chose append for my first method, I've chosen prepend for the unshift, and you'll notice I'm doing exactly the same thing. I utilize the native mutative function on my copied array. I then pass that copied array into a new list, and I return that to the user. So again, they're not going to have to deal with an immutable array. They're going to still be dealing with my immutable list. Are there questions about that one? Yes?
This mutates your object. Your mutable list function, your instance mutable list function
Yes.
is modified.
Absolutely it does. And you're like, but you're mutating something that's wrong. You're
Yes,
right.
You can't, if you do this on the same list over and over again, you're going to get different.
You can't do it on the same list. Notice what I return.
But you can save a reference to that list, call prepend, and then call prepend again on it again. So this is still mutating an object you could keep around.
That's actually true. That is actually true. So one of the costs of this kind of operation, this is a simplistic way to provide a wrapper class. It has costs. And one of the costs is that actually you are mutating stuff under the hood. And as he pointed out, in this case, what you could do is you could kind of treat it like an array where you save this value and you keep pushing stuff onto it. Now that should be prevented by the paradigm of the use of this class, but you could do that. And in fact, every time you push on change, we're using those native mutative methods, we're actually mutating an instance variable on the class, which is not a good thing. So this is like the intro. How can we just create, according to the specs that we gave, we're creating a class that does not expose any mutative methods, that does not mutate the data when you enter it, and that exposes methods for operations that are non-mutative. So we're just trying to fit those particular criteria, but what you'd want to do at the end of the day is probably come back and refactor this and extract the use of the native array functions, which we'll learn to do, and you'll know how to do by the end of this session. But you'd want to refactor that to modify this so that you're not using any array, native or mutative array functions, because they are bad, they are evil. Mutation is evil. It's a good call.
Because couldn't you just put the value into a one-M array and then concat the mutable list and return that?
Yes.
And then
You can
you're
use
not
concat to do
and there's no
exactly the same
mutation
thing.
whatsoever, still return your immutable list. So you kind of get, then you have it all, right?
Yep, you're exactly right. Concat is actually a very clever way to cheat and get this, because what concat does is it takes two separate arrays and gives you a brand new one. It's again a useful function in JavaScript to avoid mutation. So you could definitely, what you could do here is, and you have your,
I think likewise with shift, you could have done slice, right?
pardon?
You could have used slice instead of shifting for the other one.
So slice is not a problem in and of itself, but you're correct. For either the append or the prepend, both of those can be accomplished with concats evenly. You just change the placement of them. So
Right.
in this case, let's do var original is equal to 1, 2, need a comma, and then var new is equal to 3, 4. Right. Array. And now we can do original dot concat, and we can pass in new array. Like so. And this gives us 1, 2, 3, 4. So that's the way you can append a single element. Or what you can do is reverse these. 3, 4, 1, 2. So it's a way to insert items either at the beginning of a set or the end of a set without creating any mutation. But really, and we'll talk about this later on, the way you want to do this is probably recursive. The best way to do this is probably a purely functional recursive call. So, but we'll get there. So yes, this causes some mutation. It is kind of bad, but it's better than what we got to start with. And hopefully it looks familiar. Let's look at the last. Oh. Wrong key. There we go. CanCat. And this, unsurprisingly, as we just learned, CanCat does not mutate anything. So what you can do is just return a new list in which you're concatenating your current list to the list that is passed in. Because again, it's not mutating anything, we don't have to do anything special, we don't have to do any kind of cloning, we don't have to use anything else. CanCat is a very helpful function if you're to do this. What does this look like in finalized form? And again, if you've downloaded the slides, this is at your fingertips. Come on. There we go. You'll see that cat later. This thing. This is basically a cheap, semi-immutable data structure. And if we get there, we're going to come back and we're going to modify this after the fact and make this more useful. But what this does allow us to do now that is rather nice is this. New list, we pass in an entry of 1. We're going to append a 2 to it. We're going to prepend a 0 to it, and we're going to concat it with a 3, 4. You notice we're chaining those calls, and we get 0, 1, 2, 3, 4.
You know the previous, like in append, prepend, you actually modify the mutable, is that mutable, but in concat you didn't.
So, can you restate the question for me?
Yeah, so in append and prepend, you modify the mutable first, then you return a new list. Therefore, whenever you recall it, like your previous like mutable list is something different, whereas like when you did concat, you didn't modify the mutable list. That
Correct.
you had.
So prepend and append both use the native JavaScript arrays push and unshift to accomplish the same thing. We could change that to use several different methods to prevent any kind of mutation at all. Now what those are doing is those are mutating the state of the set instance variable that is the value of the original set. So yes, we're mutating both of those. Now, would you really want to avoid that? Yes. For the sake of this talk, I want to go with the simplest, most commonly known thing, which people know push and they know unshift.
But what I mean is that like if you do that concat 3, 4 and then you do that append something, like that's might not work, I think.
So you're saying if we swap this and you do a concat and then you do an append and prepend?
Yeah, that's it.
So this would, let me actually do this. Let's do this.
Because you didn't modify the mutable inside, just a bit.
Okay, so we're going to create a list, we're going to concat it, and we're going to pass in, let's just do that. We're going to concat the list, and we're going to prepend to 0. Does that work?
Let's see. I don't think it would with like.
No. And then we can call that.
So I think what we're both saying is if you save the output of the expression,
Yes.
new list.concat, and then as a variable a, and then you do a.append 0,
Yes.
a.append 0, you're going to get 2 different results.
Correct. Yeah, I think that is what I've acknowledged about both functions is that for both append and prepend is written on the screen, and we have other versions that hopefully we'll get to later. For both of those versions, they do actually cause internal mutations, such that if you save the variable of a list and you keep calling append on it, then you reference the original list instead of the values of the functions, which are in fact pure. But if you reference the original variable, you'll notice that its state has changed, and it's because it uses JavaScript mutation or array mutation under the hood. Does that make sense to everybody? Are we clear on that? Okay, good. Are there any questions about that? Good. So that can be written a lot of different ways, and you can solve that problem later. In fact, we hopefully will solve that problem later. But if you are depending simply upon the output of the values, then, which in this case we are, for instance, this function, the one that I reference in the presentation here, what you're able to do is, because from each one of those operations we're returning a list, you can continue to chain calls. So in this case, we can operate upon that list indefinitely with these operators, knowing that from each one of these we return a list that we can continue to operate on uniformly. So this is a similar syntax to what other library that's very common in JavaScript? Anyone know? Hazard guess? Nope, jQuery. So the fact that you can chain methods over a consistent object and it performs operations on that object repeatedly, this is actually something that jQuery has borrowed from the world of functional programming, where we have operations that return a value that operates consistently. So we can keep operating on those sets or on that value of sets over and over. You cannot do this in JavaScript because you have operations like push that return. I think push actually does return the merged, or I think it returns the full array, but I could be wrong. And shift does not. No, push returns I think the index, the position, right? And then shift does the same thing, whereas other things like concat will return you the whole array. In this case, we always return our immutable list. And that's why it's important in our return functions to not return something other than our list unless it's going to be a value itself, like length. All right, how many of us are lost at this point? All right, so let me help to get you unlost because I think it's important to get you there before we move on. What is the challenge?
All of it. I gotta understand
All of it? Is there one thing I can clarify?
So why can't we do this in JavaScript again?
You can do this in JavaScript, but let me show you what it looks like. Look at the number of operations I'm doing here. So I've got a list.
Yeah, 3, 4.
What does that look like without the immutable list? That's what it looks like. That sucks, frankly. Look at all the things you've got to do. Or you could do that. Which is easier to reason about? Take a list that has one member, append something to it, prepend something to it, and then concat it or join it with something else. Does that make sense to your minds? Like, is that hard to wrap your brain around? How about that?
So this is an argument for monads.
This is an argument for monads, but you need immutability, you need functional constructs for monads, you're absolutely right. This is very hard to reason about. This is error prone. This is something that if I write, and 2 weeks later I look at it, I'm going to be like, who wrote this? And I've got to try to figure it out again. This anyone can reason about. Get a list, stick something on the front, stick something on the back, and then join it with something else. Piece of cake, right? This is why immutability and monads are very, very valuable. So now, let's go on to another problem. We've created an immutable list. Did any of you actually get a full list there that could operate? Good. Talk to that guy. So again, you can download that. And what I'd suggest doing is if you have that, make sure you copy it so we can use it, because we want to add to that code later on. Ideally amend some of that code later on. But before we do that, I also want to work you guys through an immutable map. We've done it with one of the fundamental data types in JavaScript. That's the array. What's the other fundamental data type? It's the object, JavaScript object. So we can do exactly the same thing that we just did with a list with an object. We're going to change the name up a little bit, though. We're going to call it a map. We want to create a replacement for the JavaScript object class that does not mutate the initializing value of present, does not expose mutative methods, and does mimic the following methods. That is a key set and a key get, which you can do several ways in JavaScript. So we're going to set the value of a key on a map, and we're going to get it. Only 2 methods. Should be a little bit easier. Oop, I don't want to show you that yet. So do we know how to get started from here? Are we pretty comfortable with that? Or would you like me to walk through that kind of the way I did the last one? Do you want a chance to work through this yourself? Raise your hands if you do not want a chance. All right, for those of you who raised your hands, I will come up and help you. For the rest of you, please code away. Write me an immutable map that allows for a set and again. And then we'll review that when I get back.
So I forgot to clarify something in terms of setup. What you want to do, if you want to work with JavaScript, is open up the Chrome console. Chrome is best because when you use recursion, you may start crashing the browser from using Chrome. So open up the Chrome tab, open up the console, and you can write in there. That's kind of what I was doing. I would suggest that if you do that. But you're welcome. That's why you do it. That's it.
So one other thing I'm going to do here, I didn't realize in advance that the presentation I placed online would make it difficult for you to copy this code. So what I'm going to do is find our chat room and I will paste examples in there. It's room A115. And this will make it easier for those of you who would like the code. I think I might have lost my connection here. It should make it easier for you to follow along. That would be wrong. Blah, blah, blah. There we go.
How do we come to see the other channels?
You can go up here to channels, and then you can browse by them. I just searched by 115.
What was it, 115?
115, A115. Which I cannot seem to join. So that is the basic list function. Again, this is not a completely pure class. We get you halfway there, and you can modify this fairly straightforwardly if you want to use CanCat to solve the same problem. At the end of the lecture, we're going to try to solve it with recursion, which will be fun, probably. All right, so how many people are still in desperate straits on this? How many people have successfully solved the map problem? I don't want to see your hands up anymore. What is the hardest part of this problem? So there's only two methods. What's the hardest part?
Making a clone of the object.
Exactly.
We're using object assign. which
Exactly.
You can't always assume you have, right?
That is absolutely correct. So let's take a look at this guy. Huh. All right. There we go. Sorry. At the map. And what you'll notice here is that my functions are actually really simple. Can you see this? Oh, no, you can't, of course not, because it's not large. There we go. Is this well enough and visible here? So what you'll notice is that most of this, about half of this class, is taken up by the shallow copy function. And it's named very specifically for that reason. We'll talk about that later. Before, let's talk about the other functions, though. Once again, I create a toObject function that lets me actually kind of like print that out and give me the original object instead of my class. I have a set method that takes a key and a value, and you'll notice here that I'm actually, again, using mutative methods on an object, and I'm returning a new map that wraps those mutated values. You notice that my get's the same way. I'm going to actually reference that mutated or that mutative structure, the original one that we passed in. I'm going to give you the key to it. That is not a function that actually mutates anything, even though it is on the original object, because a get doesn't change anything, only the set. Now the real key to all of this is the top function, which is the shallow copy, because when I do my mutation in my set function, I'm not doing it on the original object, I'm doing it on a clone of that object. And this is a very problematic thing to do. It's problematic in the original function, though that was not as obvious during the presentation, because we were doing a slice there. That copy is simplified in JavaScript there, but it is no less problematic for reasons we will talk about shortly. So let's do this. The way that I chose to do a shallow copy, and I say shallow because we're only doing one level deep, objects can be infinitely nested, so there could be n number of key value pairs and n number of nestings within those key value pairs. So it's this unlimited problem if you're trying to do a clone. Let's say you have this. We've got an object. That's easy. This is a little bit harder. This is even harder. These kinds of problems are very, very hard to solve when doing cloning. And they're even harder because when we copy these data structures, we're using mutative structures to start with. These are all things that can be mutated. Well, not the strings, but the array here and the JavaScript objects can all be mutated. So whenever we do a clone, you're faced with the possibility that you will have impure data inside of your source. So, but this is basically what you got. You have some sort of copying mechanism. There are a bunch of different ways to do JavaScript object copies. This is a very naive one. This is basically what you got, yes? Copy over all the values, and then we wrap the mutations on that copied object when we pass in our second map. Are there any, is this unclear to anyone, what we've just done here? Good. That allows us to do, again, the same kinds of operations we performed before. We can create a map. We can set a name, we can set an age, we can set a has ring value. We can create it to a toObject, and what do we have? Pure value from pure functions. A pure value from pure functions. Now this class suffers from the same problem as the last one. It's actually not a pure class, but the methods give us exactly what we want. All right, we're going to pause here. We're at about the 1 hour mark, so we're going to take a 5 to 10 minute break. Feel free to head out I'm going to be available up here for any questions. We can work through some live coding examples before we move on from this, but please take a little bit of time, go get some water, stand up, move around, and we'll continue in just a minute.